There we go. Okay, so this is the mock midterm, and what you will see is the actual midterm is pretty, I used it as the skeleton. For those of you that came today, a slight hint for questions like these, I typically put in the lone pairs of electrons for where you're going to need to start from. So when you see lone pairs of electrons, that's probably your starting place. So that's one of the bonuses you get for coming to class. So for instance, for this one, I would put the 3 lone pairs of electrons on that oxygen because that's where we need to start our arrow pushing. Okay. Yes, these questions are fairly simple. So it is just that simple. This one, we're just going to push our arrows and pull off that proton. So this one is simply so the very first one is just and if this were on the midterm, I would have put those lone pairs of electrons there. And this one is simply just a matter of pulling off the proton, 2 sets of curly arrows. Then you have to go ahead it's just a proton transfer reaction. And so all I'm asking for, all you need to supply are these 2 curly arrows because this is already drawn. So really this is just this is actually even a kind of formative assessment. It's to get you used to pushing curly arrows. I find it makes a good first question because it gets you thinking about where electrons come from and where they're going in terms of bonding changes. So we always start at a pair of electrons. It might be a lone pair of electrons, or in this case it might be a double bond. So if we take a look at the bonding changes that are occurring here, in this example, our lone pair of electrons is going to come from the pi electrons in that carbon-carbon double bond. It's actually an aromatic system which we haven't learned about yet, but we can push our electrons, we would push them like this. So this is very helpful because you don't have to think about in terms of where that positive charge came from because we actually have it in the structure. All you have to do is supply the curly arrows. But one of the ideas is this is going to make you think about. So what's happening is these lone pair of electrons, which are in a pi bond between this carbon and this carbon, are reorganizing to form a sigma bond between this carbon and this carbon. And that we indicate that once we do that, there's the new bond that we formed. This carbon is now electron deficient and has to have a positive charge. So this is a good first question because it's easy enough, but think about it as you're doing it. It also sets you up for further during the exam to think about these things. The other thing that's nice is notice that whenever our charges balance, if we have a net negative charge in this side, we have to have a net negative charge in this side. If we have a net positive charge here, we have to have a net positive charge. If we have no net charges here, net neutral, should be net neutral over here. Now that might mean you have no charges over here and you have a plus and minus charge over here. You have a Zwitter ionic species, but overall the net is going to be the same. Okay, if we have one negative charge and one positive charge, it's overall neutral. So this first question is about building some confidence, reminding you about pushing arrows, and it's fairly typical for me to have a fairly easy first question. Then it's fair game from there on. Okay, so but you will notice there will be other questions that are fairly simple as well, and I do want to remind you, be thoughtful, but don't think something is wrong because it was easy. Sometimes things are easy. And alternatively, sometimes things are hard or difficult. So the next 2 questions are kind of right out of the classroom. Show the reaction with mechanism that occurs between pentanal and N dimethylamine under slightly acidic conditions, i.e. acid catalyst. What do you have to know here? Well, I have to know how to draw pentanal, and hopefully we do. 1, 2, 3, 4. There's pentanal, okay? You can put the hydrogen there if you want or not. I'm going to know what it is. You should also know what it is. What's N? What do we have? Dimethylamine. And dimethylamine is this thing. Let me. There we go, we're ready. This is the question. I could have drawn that. Now, a couple things. If you don't know what pentanal is, you should know that this is, you really should know what pentanal is, but you should know that it's an aldehyde. So if you don't know what it is, draw an aldehyde, okay? Because it is an aldehyde. And dimethylamine, fairly easy. We should know what and dimethylamine is. If you don't, at least draw an amine, right? There's part marks available here, so don't just say, I don't know what pentanal is. Boom, I'm done, I can't do this question. Say, well, it is an aldehyde. I'll at least draw an aldehyde, and you can get 4 out of 5, 4.5 out of 5. So there's kind of half a mark available for knowing those two, and then continue on. So in other words, try something on these, right? Don't give up. Try something. So this one's fairly easy. What do we know? Well, we get lazy as chemists, and we don't draw our lone pairs in anymore because we know they're there. And if you're uncomfortable with that, go ahead and draw your lone pairs in. You'll never be docked marks for drawing your lone pairs in, although you should know where they are. For instance, you don't want to put lone pairs that don't belong there, right? But don't forget about your lone pairs. So what's the first step in this reaction? And I need someone to tell me. So I'm trying to get some dialogue with the class. What's the first step? Whenever we see that H plus on top of an arrow, what should we do? Protonate the oxygen. That's right. Now, what's the most basic thing here? This is. So as soon as I put a little bit of acid in, it's jumping on that. But then that's just our proton carrier. That's the thing that can put protons where we need them, right? So yes, most of the time the proton's going to land on an amine. It's going to land on another amine and give us the ammonium. But every once in a while, it's going to land on here. And then, and it's okay to do this now too. I'm fine with this. You don't have to draw the molecule out all the time. In this instance, you drew it once. I know you know it. You can now go ahead and do R.
If you did the activation step and typically feel like it's actually the same step, would you get to R?
You shouldn't do that, okay? So sometimes we do things like that, but this is a case where you shouldn't do that. Why? Well, because then you have a termolecular reaction happening, and although that can happen, so in other words, if you're doing that to save time or save space, why? You should have enough room to do this, and it's not really that time consuming. And so, you're not going to get 0 on the question. You'd lose half a mark for laziness. That's it. Okay, so what do we do next? Now, we've activated our carbonyl compound. So now we just have to do a nucleophilic attack at the carbonyl compound. Okay. Now here is proton jumps on, proton jumps off. I would accept the double arrow here, but let's go ahead and say minus H plus. and then plus H plus here. So what am I doing with this minus H plus? And I'm actually moving it. I'm moving it to where I need.
So we can do a double layer and you just know that we're just going to move that proton around?
Yes. Unless I say complete mechanism. If I say complete mechanism, right? But I don't say that here. Okay? So that's fine. And for the double arrow, just for protons hopping on and hopping off, if you're moving a proton from one part of the molecule to the other, I will accept the double arrows, unless I say complete mechanism, okay? Okay, and that's kind of the only time I'm fine with the double arrows. And you don't even have to do that. The other thing you could do is go right to here and say proton shift, and that lets me know that you know what's going on, right? The double arrows lets me know what's going on. If you just have a single arrow without any explanation, I'm not really sure if you got lucky or if you know what's going on, right? So I just want to know that you know what's going on. And if in doubt, just give the complete mechanism. So now the last thing that happens is where are we? So we've moved our proton over. Oh yes. Now, okay, oops. We have to be careful here because now we can no longer do the R. Why can we no longer do the R here? Because we're doing a reaction? Yeah. What's that? Exactly. So you do want to be careful, and hopefully you realize that, because what happens if you get to here and you continue to just putting the R there, you're going to have to stop, right? And you're going to stop with a species that we're unhappy with, right? We're stopping at this species that's not going to be that stable. So then we go back to remind ourselves that it's pentanal. One, two, three, four. Okay, and now we have our proton around, our water around. We remove this hydrogen, we form a carbon double bond there, and we push our arrows there, and we end up with this thing. Let's do it this way. Okay, with this enamine. Okay, so let's say you put the R on there and you got all the way to here and you stopped here because you left the R there and you thought you were fine. Are you going to get part marks? Yeah, you'll get part marks. You wouldn't have completed, so you would, if you did everything else right and stopped there, you'd probably get 4 out of 5. This is a pretty important step. I don't need you to put the H2O in a box, although I always put it in a box to remind you that it's one of the products. That's why I put it in the boxes, to remind you that it's a product. Remember a couple things. If I can't read it, it's wrong, right? I know that seems unfair because I notice I don't draw very good ends, I know. But usually I try to fix them.
On the step where you take out the water and there's a lone pair of electrons on the nitrogen, could you just skip that process and bring in the lone pairs to make the double bond to the nitrogen and just making it there?
And sure, that would be, if you leave the charge on, you would leave the charge on the carbon in that instance. Here you're talking about, right, this step?
Yeah, so just take out the water and take the hydrogen from the carbon and just create a double bond there.
Do this in one step? Yeah, I would accept that. I would accept that because, well, yeah, you also have amines around that would do that. That's a consistent mechanism. So what he's talking about, instead of kicking off the water here, this is the equivalent of an SN1 type of reaction. similar, or I'm sorry, an E1 type of reaction. You could also have your base pull this proton, pull this proton off of here, form the double bond, and kick off the water all in one step, and that likely happens too. Both would occur. So what we are looking for are things that make chemical sense. Okay? So what makes chemical sense? Actually, there's a good example. No, it's not a good example. The reverse would be an example. So what makes chemical sense? Thermomolecular reactions usually don't happen unless one of the molecules or two of the molecules are solvent molecules, right? Because then you have lots of them, and they're going to be around. So sometimes you get reactions of 3 species meeting, but one of those would have to be a solvent. Otherwise, it's very, very unlikely that 3 things are going to collide at once. So if it's your solvent and 2 things collide, the solvent's right there, you can have thermomolecular reactions occurring. Although it's still actually kind of unlikely, and it's still probably stepwise. Okay, the one thing that may have been a slightly bad example in this test is the next question is actually pretty similar. Oh, I'll leave that there. The next one is show the reaction with mechanism that occurs between benzyl methyl ketone. Notice too the hints that are in here. For instance, I might be asking you to naming things, and if I asked you to name, if I named something ethyl methyl ketone and you didn't know how that worked, down here I'm giving you benzyl methyl ketone, right? Here's the benzyl group, here's the methyl group, and the ketones in between. So there are answers hidden within, and it's impossible to write an exam without those clues being in there. So in other words, you should probably, if you're struggling, you should go through things. Don't start at 1 and go to 2 and then stop because you can't get past 2. If you're stuck on 2 for a bit, go to 3. So the next one is very similar. And we now have this thing and an H+, and already we're thinking right away activation of our carbonyl. So we activate our carbonyl, and I'm going to move my other species around. It's now the nucleophile. So here, I'm going to say proton shift, because we just did it, and now this is an example. I need to move this proton from here to here. Okay. Now this is an instance where it is much more likely to all happen at once. It's an intramolecular reaction. In other words, we don't just take, oops, I made a mistake. Similar in vein to what you've been discussing. In this one, the water's not going to leave followed by collapse of the carbocation. It's all going to happen at once because it can happen intramolecularly. So here we get pH let's put our H2O in a box, and now finally we have minus H+. So again, we're talking about things that make chemical sense. This is a second half organic chemistry, and some of the things I do expect that you realize this would happen intramolecularly rather than leave, give us the carbocation followed by collapse. And that's not a big mistake. If you did it the other way, would you get it wrong? It's kind of a concept from last semester, but because this is an intramolecular reaction, it happens very fast. In other words, this doesn't have to diffuse and meet that species. It's right there. So intramolecular reactions happen very quickly. What we could have done for this step is we could have removed water, I suppose. So from here, where we have pH, OH, H plus, we could have said minus H plus. And I'm going to draw it this way. And made our carbocation, and then drawn this. So this is an unlikely chemical event because it's just going to go all at once.
Just to clarify, was this on any of the slides?
Yes.
Really?
This is the protection of a ketone.
Well, like,
I just don't think we ever went over the mechanism specifically.
yeah, it gives us just a plain reaction, but it doesn't give us the mechanism at all.
Really?
It just gives us the.
Okay, so you never saw this reaction mechanism?
I think actually what it gives the information on acetal, but not the cyclic acid.
But we went through this, didn't we?
We went through things similar, but not explicitly in the reaction.
Right. That's right. Yeah. I actually, part of the coming to university is the critical thinking. Sometimes you're going to ask to do things that you haven't done exactly. We also probably never specifically dealt with this molecule, right? Okay. We did do this reaction, right? The formation of acetals.
Yes.
We did specifically.
Yes.
Okay. So this is just the formation of an acetal where both of our alcohols are on the same molecule. Okay. So I do want you to realize, though, that you are going to be asked to do things that you may not have done exactly, right? Okay. And that's your utility in the world. Is we have to figure things out. We have to do some problem solving. Okay. So yes, we never dealt specifically with that particular reaction. Okay, so these reactions, we've kind of gone over this particular reaction. One of the things to be careful here is this is an alkyl magnesium bromide and an epoxide, and this reaction happens fairly rapidly. And now one of the things you may want to do, I'm going to go all the way over here. We're forming a bond between here, and we're breaking this bond. So you might find it helpful to leave the shape there. Okay, so that's helpful in making sure that you make this bond, right? One of the things that we see a lot is that is this, okay? That's confusing. Okay, so I'll do it this way. It does not give this compound. Okay, it may look like it gives that compound, but count your carbons. 1, 2, 3, 4, 5. 1, 2, 3, 4. You got 4 there. You have 5 here. Don't forget to count your carbons. So that's the first step in this reaction. That's number 1. Then number 2 is H plus H2O. And then that's followed by PCC. So this is our final product. 1, 2, 3, 4, 5. That's all I'm looking for, is that. So all I'm looking for is the products in these reactions. So if you might want to work on the back of your sheet or bring in, you can bring in empty scrap paper. Okay, so this says show the organic products for each of the following reactions. Do not include inorganic products or the mechanism. I just want the products. So this one, hopefully you see 1 in diethyl ether. 2, it's just the workup. 3 is the oxidation with PCC, which we know oxidizes primary alcohols to aldehydes. And it will oxidize secondary alcohols to ketones, but the important thing is that it will stop at the aldehyde for primary alcohols, that last step. So once we understand that, the next reaction, fairly simple. How many people think they know the product for this reaction? Okay. What is it? It is the alcohol. Slight mistake there. I probably should have had the workup there, okay? If the workup isn't there, I probably made a mistake. Raise your hand. Go ahead and ask. And if I make the mistake, I'll mark either one of them right. Okay? I just realized now that I didn't have the workup there, but normally I would. Okay? Oh, that is another thing. If you have a question, go ahead, raise your hand. And the worst thing I will ever do, I won't yell, I won't scream. I might say I can't answer that question. That's the worst outcome for asking a question. Okay? So if you have any questions, go ahead and ask. And the nice thing is, if you asked, I would then announce to the class, oh, I made a mistake there. There should be a workup there. So then it helps. Because if you have a question, others may have that same question. So whenever I give a student a piece of information, I announce it to the class. So if I say, oh, water, then I'll tell the whole class, there's water there. The next one, NaCN, slow addition of H2SO4. So our CN is our nucleophile that adds, and then the H2SO4 just protonates, so that's the cyanohydrin synthesis. This is the tricky one here, okay? Here we have a diketone and a diamine. What do you suppose that reaction product is? So what do we know about and we've never asked this in class, but I would expect you to be able to figure it out. RNH2 plus catalytic amount gives us this. Gives us the imine, right? So in this particular instance, we have this thing. If it helps, draw it like this. We're going to form an imine between this nitrogen and this carbon, and an imine between this nitrogen and this carbon, and we get this. That's the product, okay? So, yes, we haven't seen it before, but yes, we are equipped to handle that question if we've been going to class. And the final reaction, SOCl2, what do we make in one? We make an acid chloride. And in the second step of the reaction, we're throwing ethanol in. We're just replacing that OH with CH2CH3. We're making the ester here. Okay, and that was chapter 17. I'm going to skip this. These are, again, most of them fairly easy. I'm going to skip them because I want to get into the next couple. We only have 13 minutes or so left. You can see it's draw the structure for propyl ethanoate. That should be fairly easy. Provide an acceptable name. Not that hard. This, I would probably name this as an aldehyde, in which case that's carbon number 1, 2, 3, 4, 5, 6, 7. So it's heptanal, and then put the substitution on. This is an alcohol. Count your longest chain. 1, 2, 3, 4, 5, 6, 7, 8. So it's an octanol with a couple of methyl groups on it. So it's dimethyl octanol, and you just have to get the positions in there. You would number this 1, 2, 3, 4, or 1, 2, 3, 4, 5. So this is number 1, because you always name it. If you name it an octanol, the OH has to have the lowest possible number. These we should be able to do. So it's +1 for each of the carbon-oxygen bonds on that carbon. So the oxidation number there is +2 because it's bonded to oxygen twice, and then it's bonded to carbon twice, which means we don't add anything to it. So that oxidation state of that is +2. What's the oxidation state of that starred carbon? -2, correct, yeah. Point to the most, I said I wouldn't do it, and now I'm doing it because it's so easy. Point to the most electrophilic carbon. Please don't be ambiguous with your pointing, be bold. We've talked about the electrophilicity of aldehydes versus ketones, and we also talked about the fact that these are not particularly electrophilic and they're unreactive because of the resonance structure we can draw with the lone pair of electrons on the nitrogen. We can draw a resonance structure where we have a carbon-nitrogen double bond and it's Zwitter ionic species. So that's not as electrophilic as that. That's the most electrophilic carbon. Over here, we have these two kind of look the same, and the big difference is that we have an electron withdrawing group attached directly to that carbon. We talked about these being the most reactive of the carboxylic acid derivatives. So that is the most electrophilic carbon. Circle the strongest acid for each step below. How many people think they can do this one? Okay, so we put an electron withdrawing group. We left it alone. This isn't even an acid, okay? I should say this doesn't even have the name of an acid. It is an acid. That OH is very, very slightly acidic, but we don't call it an acid, so we can probably throw that one off. Okay, so we have to pick between these two, and it's this one because we have the very electronegative atom bonded right to it. Down here, we have an acid. We have phenol. This is right from class. We know that this acid is more acidic than this phenol. Okay, but what's this? Sulfuric acid. What do we know about sulfuric acid? Strong acid. Carboxylic acids, are they strong acids? They're weak acids, right? They don't completely ionize in water. Sulfuric acid completely ionizes in water. Okay, so that's the strongest acid. This is right out of the notes from class. So we are asked to do the basic hydrolysis of show the mechanism for the hydrolysis of ethyl benzoate under basic conditions. There is quite a significant concentration of water. So under basic conditions in water, we should know that our reactive species is going to be OH minus. Okay? That's the hint there. So that's, you know, if it's hard at all, someone's going to ask me what the base is. If you raise your hand and said, what is the base? I would say, well, you should be able to figure that out. Basic conditions in water, the base is going to be hydroxide. So we have hydroxide, we have this, and we have an arrow, and we form our tetrahedral intermediate. What might I be expecting in this question? I would be expecting that you're going to understand the equilibrium is important here, okay? And I'll get to that in a minute after I draw it. In case I forgot the... Yes. Very good. As you can tell, I lost a lot of part marks on exams when I was a student. Okay, so what happens with this now? We're just going to reform our carbon-carbon double bond, and we realize it could go back that way. Maybe at this point we realize that equilibrium is important. Maybe we don't. Maybe we right away go to this. Okay, at this point we realize I have an acid and I have a really strong base. What's this base going to do? Most likely it's going to rip off another proton from water and give me hydroxide back, but that's okay because hydroxide is going to do the same thing. Either way, when this or when hydroxide meets this carboxylic acid, we just get this. And the alcohol. So then I go to the rest of the question. Is sodium hydroxide needed in a catalytic or a stoichiometric amount? My sodium hydroxide is needed. Oh, there's another hint about the base. Actually, I didn't realize I put the base in there after. Okay. I should have said, is the base needed in a stoichiometric or equivalent amount? Well, if we take a look, we end up using up our base. So the answer is we need a stoichiometric amount. It's not catalytic. And the next says, what drives this reaction to completion? Then we should clue in, oh, this is probably an equilibrium reaction. And this is the point where whenever these two meet, they don't go this way. Okay? So it's kind of at this point. This is the reaction that drives the reaction to completion. But when a strong base meets a carboxylic acid, a relatively weak acid, it's just going to do an acid-base reaction and it's going to stop there. Okay? So notice I say answer these two questions using a well-written sentence or two in English. I will take half a mark off if it's a horrible sentence. Okay? And the reason for that is because you should be able to give me a couple of sentences that convey something relatively easily. When I worked in industry, one of our biggest problems is that we have to communicate effectively, and if we can't, we're not going to advance. That happens no matter what job you have. So I always do this just to remind people that writing in English is important here.
What did you say the answer was to what drives the reaction to completion?
What drives the reaction is the fact that we have a strong base reacting with a carboxylic acid. This is a case of a weak acid strong base. Remember from first year. And the base is strong enough that this reaction goes to completion. And in other words, there is no equilibrium in this last step. Okay? If I had a weak base like a very weak base, that would be significantly equilibrium. The whole thing would end up being equilibrium. And the final one, hopefully, so you may have difficulties coming up with the exact sequence of events to get here, but that's okay. There's part marks available here. I'm looking for some things. I'm looking to realize that hopefully you can tell that somehow I have to clip this to this carbon, right? Okay? Do we have any reactions in our arsenal that allow me to just clip this to this carbon directly? No. No, we don't. We have to convert this functionality to something that will react with either this or something I can make from this, okay? When we have to form a carbon-carbon bond, at this point, how many reactions have we done that form carbon-carbon bonds? We do nucleophilic additions to carbonyl compounds for forming carbon-carbon bonds. That's all we've covered so far this year, right? Grignard reagents, can we make a Grignard reagent from this? Yeah, okay? So, what if we make that an aldehyde? Okay, we can do that. We can react that with PCC, react with an aldehyde. Oh, is there any problem? So I make this into an aldehyde. What's my problem? I need to protect this thing, right? Because that's also going to react with the Grignard reagent. So if I make my aldehyde first, can I then protect just that carbonyl? No. So I have to protect that carbonyl first. Okay? So we have to think about protecting that carbonyl, converting this to something we can form a carbon-carbon double bond with, making this into something nucleophilic. Okay? So what we want to think about then is we talk about retrosynthetic analysis working backwards. Really, in synthesis, we work backwards and forwards at the same time. We know what reactions can I do. But here, the first thing we need to be thinking about is clipping those two molecules together. So I might think, when I look at my compound, I might think, well, I could make this from this. Need to protect. Okay? I need to protect just this. I can't protect both of them. So maybe I need to protect it before I get there. So then I should be thinking, okay, well, this is still good. This will actually give me that, everything. So I can easily make this right away. The next thing I think, well, I have to protect that. So I have to make this compound. We only know one way of protecting. I need to make that. How am I going to make that? I'm going to make that. These are retrosynthetic arrows, the big thick arrows. I can make that from this. Okay, there we go. I can make that from this, and I can make this. Sorry. Your question? Someone? Yeah.
Would you be able to put the conditions in?
Actually, for what I would do now that I figured it out, now I would start from the beginning and put the conditions in. Okay? So right now I was just analyzing what do I know, how can I make this? Without the conditions, not worrying about the conditions. Now I'm going to say, okay, how do I make that from this? Now I put the conditions in. So now I'll put them in. So we would start off with this compound, and we would react this with and a catalytic amount of H+, and that gives me this compound. We could react this with PCC. We have to be gentle with our PCC. We can do this reaction. One of the problems of this is that some of this is actually going to deprotect. That's going to happen. But we can actually do it and purify it after. Once we have this compound, oops, that was bad. Okay, we need to react this and we can make that okay. So we use this route to make this thing. We use this route to make this. Then we react these two compounds at the end. So I'm going to, 1 in ether, 2 H plus H2O. And in fact, that's the nice thing about this reaction. That's all going to happen at once. You're also going to deprotect this when you work this up. So there we go. This kind of happens all at once, okay, via here. The H plus H2O, that's what you use to deprotect this. So the last step actually works very nicely to deprotect everything. Okay, so again, this is something where we're expecting you, and in terms of, this is probably the hardest question on the exam. And I expect almost all of you should be able to get some part marks on the hardest question.